You've tried to understand how neural networks actually learn, right? You open a textbook, you click on a video, and within minutes, you're drowning. Backpropagation, stochastic gradient descent, the chain rule. It feels like an impossibly complex black box, a machine that just performs magic, and you're told to just accept that it works. Here's the secret. You've been taught this the wrong way around. The entire engine that powers all of modern AI is built on just a few simple, incredibly intuitive ideas. Here's the first one. Idea number 1, the valley. How do you find the bottom of a valley when you're stuck in a thick fog? And idea number 2, the blame game. How do you figure out who to blame when a team project goes wrong? Once you truly grasp these two concepts, all of that scary math suddenly clicks into place. It's not a barrier. It's just the language we use to describe a logic you already understand. So, here's my promise to you. Give me 40 minutes and you will master how neural networks learn. We will go step by step, building the entire learning process from scratch. No skip steps, no magic. By the end of this video, you will have a deep, foundational understanding of neural networks. You won't just know the buzzwords. You will finally get that aha moment. All right, let's get straight to the code. Look at this. It's an input function, an output, and a simple loop that runs 100 times. This tiny loop right here, this is the beating heart of every single AI system you have ever heard of. ChatGPT, Midjourney, self-driving cars, they all run on this exact logic. So, what is it doing? Every neural network is trying to get better by minimizing its error. That's the gap between its guess and the right answer. This algorithm is the engine that drives that error down to 0. And the intuition is dead simple. Remember that foggy hill I mentioned? You're lost. You need to get to the bottom of the valley, but you can only see your own 2 feet. What do? You don't need to see the whole map. You just 1. Feel the slope right where you're standing. 2. Take a small step in the steepest downhill direction. And 3. Repeat. That's it. That's gradient descent. You just feel the slope, take a step, and do it again and again until you reach the bottom, where the ground is flat. Our algorithm does the exact same thing, but with math. Let's make this crystal clear with an example. Imagine our valley is this perfect U-shape, described by the function you see here, f of x equals x squared. The gradient, which is just a fancy word for the slope, is found with a derivative. Check out this formula. For x squared, the derivative is just 2x. This is our slope detector. Think about it. If we're standing at x equals 3, the slope is 2 times 3, which is 6. It's a positive slope, which means downhill is to the left. Now, what if we're at x equals negative 2? The slope is 2 times negative 2, which is negative 4. A negative slope means downhill is to the right. And what happens at x equals 0? The slope is 0. The ground is flat. You've arrived. Now look at the update rule. This little formula just automates the whole process. It subtracts the slope, forcing x to always move downhill towards the minimum. Let's watch it in action. We'll start at a random spot, say x equals 3, and we'll use a small step size, which we call the learning rate, of 0.1. Okay, check out this table. We are going to walk through this together, step by step. First, at iteration 0, our current x is 3. The error, which is x squared, is a huge 9. The gradient, 2x, is 6. So the new x is our old x, 3, minus our step size, 0.1, times that gradient of 6. 3 minus 0.6 is 2.4. That's our new position. See how that works? Now for iteration 1, we start at 2.4. The error has already dropped to 5.76. we repeat the process. Calculate the new gradient, take another small step, and we land at 1.92. I'm not going to go through every single line, but you can see the results here. Look at that. We started at x equals 3 with a huge error of 9. After just a few steps, it's plummeting. The algorithm is literally sliding down the curve of the parabola. But here comes the plot twist. Gradient descent has tunnel vision. It only sees the slope directly under its feet. What if the landscape isn't a simple valley? What if it's a function like this one, with lots of bumps and dips? As you can see on the graph, there's a true global minimum, the deepest point. But there's also a shallower trap, a local minimum. So if you start at x equals 0.5, the algorithm slides into the shallow valley and gets stuck. It found an answer, but not the best answer. But if you start at x equals negative 0.5, it finds the true deep valley perfectly. Same algorithm, different starting points, wildly different results. This raises a terrifying question. A neural network has millions of parameters, creating an error landscape with billions of these traps. How could this possibly work for GPT-4? Here's the surprising, almost unbelievable answer. For huge neural networks, it almost doesn't matter. This is the surprising luck of high dimensions. It turns out that most of those local minima, those traps, are actually pretty good solutions. And the truly bad traps are incredibly rare. It's one of the luckiest coincidences in the history of AI, and we're still trying to fully understand why. Empirically, gradient descent just works. Now you understand the core engine. But so far, our valley only has one dimension. We can only move left or right. A real neural network is like a massive soundboard with a million knobs to tune. How do you adjust all of them at once to find the perfect sound? How do you figure out the slope in a million different directions simultaneously? The answer is surprisingly elegant. You don't. Instead, you figure out the slope for each knob individually, as if it were the only one you were turning. You focus on one knob at a time, listen to its effect, adjust it, and move to the next. This is the core intuition behind one of the most important tools in machine learning, the partial derivative. When our function has multiple variables, we can't just ask for the slope. We need to specify which direction we're talking about. This is where we use the partial derivative symbol. Look at this. When you see this first formula, it's asking for the slope in the x1 direction only. And for the other direction, the second formula asks for the slope in the x2 direction only. Simple as that. Let's upgrade our valley to a 3D example with this function. Check it out. F of x1, x2 equals x1 squared plus 2 times x2 squared. This creates a beautiful oval-shaped bowl. The lowest point, as you can probably guess, is right at the origin, at 0, 0. So how do we calculate these partial derivatives? Here is the one magic rule you need to remember. To find the partial derivative with respect to one variable, you treat all other variables as if they are just constant numbers. That's it. Let's try it. Look at our function again. We want to find the partial derivative with respect to x1. First, we pretend x2 is frozen. That means the whole term 2 times x2 squared just becomes a constant. And what happens when we take the derivative of a constant? It disappears. It goes to 0. So all that's left is x1 squared, and the derivative of that is just 2x1. That's our answer. Easy, right? Now let's do the other one. Let's find the partial derivative with respect to x2. This time we pretend x1 is frozen. The x1 squared term becomes a constant, so it vanishes. We're only left with 2 times x2 squared, and the derivative of that is 4x2. You've just calculated a multidimensional gradient. With this tool, our gradient descent algorithm gets a simple upgrade. Instead of one update rule, we now have one for each variable. And here's the key. We apply them all at the same time. Check out the algorithm. It's almost the same as before. For every iteration, we calculate the gradient for x1, we calculate the gradient for x2, and then we update both x1 and x2 using their own gradients. Let's navigate our 3D bowl. Our function is x1 squared plus 2x2 squared. We'll start at a random point, let's say 3, 2, and we'll use a learning rate of 0.1. Let's see. The initial error at our starting point is 3 squared plus 2 times 2 squared. That's 9 plus 8. A big error of 17. Let's watch the algorithm work. Okay, check out this table. We are going to walk through this together, step by step. At iteration 0, our starting point is x1 equals 3, x2 equals 2, and the error is 17. Now for the gradients, remember our formulas? The gradient for x1 is 2x1, so that's 2 times 3, which is 6. The gradient for x2 is 4x2, so that's 4 times 2, which is 8. Now we update. The new x1 is the old one, 3, minus our learning rate, 0.1, times its gradient, 6. That's 3 minus 0.6, giving us 2.4. For x2, it's the old value 2 minus 0.1 times its gradient, 8. That's 2 minus 0.8, giving us 1.2. Our new position after one step is 2.4, 1.2. Now for the next iteration, we do the same thing. I'm not going to repeat all the details, but you can see the process in the table. The error keeps dropping. Look at that beautiful convergence. And that very first step, the gradient told the algorithm how to move in both the x1 and x2 directions, and it slashed the error almost in half in one go. As it gets closer to the bottom, the slopes get smaller, so it automatically takes smaller, more careful steps. x1 and x2 both spiral down towards 0, perfectly finding the minimum of our 3D bowl. This is it. This is the fundamental technique for training a neural network. We treat every single weight as its own knob. We calculate its partial derivative, its individual contribution to the total error, and then we nudge it slightly in the right direction. Scale this up from 2 knobs to 2 million, and you have modern machine learning. But this raises a new, much more subtle problem. In our bowl example, x1 and x2 directly affected the final error. It was simple, but in a deep neural network, a weight in the very first layer doesn't directly touch the final error. Its influence travels through a long, complex chain of calculations. How do you calculate the blame for a single knob when its effect is buried 20 layers deep? This is the single biggest problem in deep learning, and its solution is one of the most elegant ideas in all of mathematics: the chain rule. Look at this formula. It's so simple. But this simple formula is the masterstroke. It's what makes deep learning possible. And the intuition behind it, it's literally a blame game. Imagine your team's final presentation fails. That's the error. To find out why, you trace the problem backward. First, the presentation was bad, which happened because the slides were confusing. Let's say the slides get 50% of the blame for the bad presentation. And the slides were confusing because the data analysis was flawed. We'll say the analysis was 80% to blame for the bad slides. And that was because the initial data collection was sloppy. Let's say that gets 90% of the blame for the flawed analysis. So, to find out how much the initial data collector is responsible for the final failed presentation, you just multiply the blame at each step. 90% times 80% times 50% equals 36%. The chain rule does exactly this. It multiplies the influence at each link in the chain to find the total impact of a variable far, far away. Let's see this mathematical blame game in action. Look at this beast of a function on the screen. This looks intimidating, right? But we can break it down. First, we calculate a variable u, which is 2 times 1 plus time 2. Then, we calculate v, which uses u in its own formula. And finally, the result f is just v cubed. You can see the chain of influence clearly in this diagram. x1 and x2 influence u, which influences v, which finally influences f. Okay, let's find the derivative of f with respect to x1 by tracing the blame. Look at the table here. We're going to walk through this step by step. Step 1. How much does f blame v? Well, f equals v cubed. Using the power rule, the derivative is just 3v squared. Simple enough. Step 2. How much does v blame u? The function for v is u squared plus 3 times 2 squared. When we're taking the derivative with respect to u, we treat x2 as a constant, so the derivative is just 2u. Step 3. How much does u blame time 1? The function is u equals 2 times 1 plus time 2. The derivative here is just 2. So, what's the total blame? We just multiply everything together. As the formula shows, it's 3v squared times 2u times 2, which gives us 12uv squared. And that's our gradient for time 1.
Now for the derivative with respect to x2. It's trickier. Why? Because x2 influences v in two ways. Indirectly through u, but also directly. You can see both paths in this new diagram. The total blame is just the sum of the blame from all paths. Let's break this down using the table. The overall derivative is the derivative of f with respect to v times the derivative of v with respect to x2. We already know the first part is 3v squared. So we just need to find the total derivative of v with respect to x2. First, the indirect path through u. The chain rule tells us to multiply the derivative of v with respect to u by the derivative of u with respect to x2. That's 2u times 1, which is just 2u. Next, the direct path. This comes from the 3x2 squared term in the formula for v. The derivative of that, 6x2. So the total derivative of v with respect to x2 is just the sum of both paths, 2u plus 6x2. And our final result for the gradient, we just multiply it all together, 3v squared times the quantity 2u plus 6x2. And just like that, the chain rule has untangled that complex nested function for us. Now look what we can do. Check out this code snippet. We can plug these gradients we just found right into our algorithm. For 100 iterations, we calculate the blame for each variable, grad x1 and grad x2, and then we nudge each variable in the right direction using our learning rate. This is the key. The chain rule gives us a systematic way to find the gradient for any variable, no matter how deeply it's buried inside a complex function. This is the final piece of the puzzle. 1, we know how to go downhill using gradient descent. 2, we know how to find the slope for each individual knob using partial derivatives. And 3, and now we can trace blame through a long chain using the chain rule. We have all the mathematical tools we need. Now it's time to stop playing with abstract functions. Let's use these tools to build our very first functioning AI brain and watch it actually learn right before your eyes. So what even is a neural network? Forget the hype, forget the sci-fi. It's just a collection of simple functions called neurons organized in layers. That's really it. Each neuron is just a tiny calculation, nothing magical. Think of something as simple as f of ab equals a plus b squared. We stack them in layers, kind of like an assembly line. This creates what we call a forward pass, a one-way flow of information, starting from our data and ending with an answer. You can see it in this diagram. Information moves from the inputs through layer 1, then layer 2 to the final answer. So let's build one right now. Here's the architecture for our very first AI brain. Our network has 2 inputs, 2 hidden neurons in the middle, and 1 final output neuron. To make it work, it has 5 tunable knobs, or weights, which you can see here as W1 through W5. Look at these formulas. This is the exact math our brain will use. The first hidden neuron, H1, is calculated using this first formula. The second one, H2, uses the second formula. And finally, the output neuron combines the results from H1 and H2 to produce our final prediction. The iteration shows how all these pieces are connected. Now, let's give our new brain a task. We want it to learn a new function, specifically this one, f of x1, x2 equals 2x1 squared plus 3x2. To To do that, we'll collect 3 training examples. You can see them in this table. For an input of 3, 2, the true output should be 24. And you can see how we got that. 2 times 3 squared plus 3 times 2, that's 18, plus 6, which is 24. We did the same for the other 2 examples. Okay, let's get set up. Right now, our network is an untrained brain. It's a blank slate. We have our training examples, and we have the architecture we just designed. The weights are what the network uses to learn, but to start, we just pick some random numbers. Let's just use these initial weights. W1 is 1, W2 is 2, and so on. This next step is called the forward pass. We're just going to feed our inputs through the network and see what comes out the other end. There's no learning happening yet. This is just pure calculation. Let's look at the results. Remember, our weights are set to 1, 2, 1, 1, and 0. The formulas are on the left. Okay, let's walk through this entire process together, step by step, for the first example. Our input is 3, 2, and the true answer we're hoping for is 24.
First, let's calculate h1. The formula is x1 plus w1 times x2 all squared. So that's 3 plus 1 times 2, which is 5. 5 squared is 25, so h1 is 25. Next, h2. The formula is w2 times x1 times x2. That's 2 times 3 times 2, which gives us 12. And finally, our predicted output, y. We combine h1 and h2 using our other weights. The formula is w3 times h1 plus w4 times h2 plus w5. So that's 1 times 25 plus 1 times 12 plus 0, which gives us a final prediction of 37. The true answer was 24. Our network guessed 37. The difference is 13. Now that we've done the first one, the rest are similar. For the second example with input 1, 4, the network predicts 33. The real answer is 14, so it's off by a whopping 19. For the last one, it's a bit closer. It predicts 13 when the answer is 11, for a difference of just 2. Ouch. Not great. For that second example, it was off by a massive 19 points. But how do we quantify this failure? We need a single number that tells us overall how wrong our network is. We can't just add up the differences, because a negative 19 and a positive 19 would cancel each other out, making it look like the network is perfect when it's actually terrible. The solution? We square the differences. Here's why squaring works so well. First, it makes every single error positive. No more canceling out. That error of negative 13, when squared, becomes a positive 169. Second, and this is really important, it punishes big mistakes. A small error of 2 gets a penalty of 4, but that huge error of 19, it gets a massive penalty of 361. So let's calculate the total squared error. We take each of our differences, square them, and add them up. That's negative 13 squared plus negative 19 squared plus negative 2 squared, which is 169 plus 361 plus 4. Our total squared error is 534. There it is. 534. That is our antagonist, our enemy. Our goal for the rest of this video is to make this number, 534, as close to 0 as possible. We've officially completed the forward pass. Our network has made its first terrible predictions, and now we've measured its total failure. Now for the aha moment. We're going to take all the tools we've learned, gradient descent, partial derivatives, and the chain rule, and unleash them on this network. Remember the blame game with the chain rule? That whole idea of tracing responsibility back through a complex chain of events? And remember that crazy nested function we used as an example? This one right here. Here is the single most important insight of this entire video. A neural network is just a giant nested function. That's it. That's the whole secret. Look at this comparison. Math functions have nested operations like f of g of h of x. Neural networks have layered operations like layer 2 of layer 1 of the inputs. It's the same structure. For our math functions, the variables we controlled were x1 and x2. Our goal was to find the values for them that minimize the function's output. But for a neural network, what are the variables? What are we trying to minimize the error of? This raises the most critical question. What are the knobs we are allowed to tune in our neural network? What are the variables? Is it the inputs, x1 and x2? No, absolutely not. The inputs are the data we're given. We can't change the fact that we were given the input 3, 2. That's the problem we have to solve. We can't just change the problem. The only things we have control over, the only knots we can turn, are the weights. W1, W2, W3, W4, and W5. This is the breakthrough. Let's look at that comparison again, but for real this time. In our math problems, we controlled x1 and x2 to minimize the function. In our neural network, we control the weights, W1, W2, W3, W4, and W5, to minimize the error. We're not trying to find the best inputs. We're trying to find the best weights that turn the inputs into the correct outputs. And we already know exactly how to do this. We use gradient descent to find the values of our variables that minimize a function's output. The process is identical. It's time to play the blame game. Let's focus on that first terrible prediction. You can see the crime scene laid out here. The input was 3, 2, the target was 24, but our network predicted 37. The error was a massive 169. Let's start the investigation with our first suspect, W5. Its path to the error is short and direct. As the diagram shows, the error comes from the prediction, and the prediction is directly influenced by W5. So how do we find out how much W5 is to blame? We use the chain rule. Look at this formula. The derivative of the error with respect to W5 is the derivative of the error with respect to the prediction multiplied by the derivative of the prediction with respect to W5. Let's do this step by step. First, the derivative of the error with respect to the prediction. The error formula is y true minus y pred squared. So its derivative is 2 times y pred minus y true. Plugging in our numbers, that's 2 times 37 minus 24, which gives us 26. Second, the derivative of the prediction with respect to W5. The prediction is W3 times H1 plus W4 times H2 plus W5. So the derivative with respect to W5 is just 1. The total blame for W5? It's 26 times 1. 26. Now for a tougher suspect, W1. It's buried much deeper. Its path to the error is longer. The error comes from the prediction, which comes from H1, which is affected by W1. This means more chain rule steps. Here's the longer formula. We need to find the derivative of the error with respect to W1. Let's walk through it. First, the derivative of the error with respect to the prediction. Wait a second. We already calculated this. It's 26. We don't need to do it again. Next, the derivative of the prediction with respect to H1. Looking at the formula, that's just W3, which has a value of 1. Finally, the derivative of H1 with respect to W1. The formula for H1 is x1 plus W1 pounds x2 squared. Using the chain rule on this little piece, the derivative comes out to 2 times x1 plus W1 pounds x2 times x2. Plugging in the numbers, that's 2 times 3 plus 1 times 2, which is 2 times 5 times 2, giving us 20. So the total blame for W1, it's 26 times 1 times 20. That's a whopping 520. Now stop. Look at what we just did. Look closer. Here are the two blame calculations we just performed. Do you see it? The term for the derivative of the error with respect to the prediction, that value of 26, it's in both calculations. This is the multi-trillion-dollar trick that makes deep learning efficient. We don't recalculate everything from scratch for every single weight. We calculate the error gradient once, at the very end, and then we propagate it backwards, reusing calculations every step of the way. This is backpropagation. It's not magic, it's just being clever and not redoing work you've already done. We can systematically find the blame for every single weight. Look at these formulas. We calculate that first error term, the derivative with respect to y pred, and then we just keep multiplying it backwards through the network. We calculate the gradient for the output weights, then we use those results to help calculate the gradients for the hidden layer, and then use those to calculate the gradients for the hidden layer weights. You can see the flow in these diagrams. The forward pass computes the output with data flowing from left to right. Then the backward pass computes the gradients with the error signal flowing from right to left, propagating backwards. So here are all the calculations in one place. We start with that initial gradient of 26. We use it to find the blame for W5, W4, and W3. Then we propagate that blame back to find the blame for H1 and H2. And finally, use that to find the blame for W2 and W1.
Whew!
It's a beautiful cascade of reused information. Okay, we have our gradients. We have the exact blame for each of our 5 knobs. Now we just take one step of gradient descent. We'll use a tiny learning rate of 0.0001. The update rule is simple. The new weight is the old weight minus the learning rate times the gradient. Very good. Look at this table. For W5, the old value was 0. The new value is 0 minus our learning rate times 26, which is negative 0.0026. For W4, the old value is 1. We subtract the learning rate times its gradient of 312, and we get 0.9688. We do this for every single weight. That's it. The learning has happened. We played the blame game, and we commanded each weight to adjust itself. But did it work? This is the moment of truth. Let's do another forward pass, but this time with our new updated weights. Let's calculate step by step. H1 is now 3 plus 0.948 times 2 squared, which gives us about 23.97. H2 is 1.9844 times 3 times 2, which is about 11.91. And finally, the new prediction. We plug in all our new weights and new hidden values, and we get a final prediction of 33.95. Let's compare. Before learning, our prediction was 37. After just one update, it's 33.95. The target is 24. We were 13 units off, and now we're only about 10 units off. Yes, it worked! The prediction moved from 37 down to 33.95. It got closer to the target of 24. The error got smaller. This is not a guess. This is not magic. This is intelligence emerging directly from mathematics. By following the chain of blame backwards and nudging our parameters downhill, the network learns automatically. Repeat this process 1,000 times, and it will get even closer. 1,000,000 times, and it will be nearly perfect.
But hang on. Think about what we just did. We trained our network on one single example, the case where 3-2 should equal 24. That's like studying for a final exam by memorizing the answer to a single practice question. You might ace that one question if it shows up, but you haven't really learned the concept. You'll fail the actual test. To become truly intelligent, our network can't just memorize one data point. It needs to find the underlying pattern that works for all of our examples. So the next logical question is, how do you learn from the entire crowd of data at once? There are 2 main strategies for this. On one hand, you have online learning. This is what we just did. You look at one example, you calculate the blame, and you update the weights immediately. Then you move on to the next example. On the other hand, there's batch learning. Here, you look at all the examples first. You calculate the blame for each one, then you add up all the blame from everyone, and only then do you update the weights just once at the very end. Check out how the algorithms look side by side. The online learning formula loops through each example and updates the weights inside the loop. It happens immediately. But the batch learning formula is different. It loops through all the examples just to add up the gradients into one big total gradient. The weight update only happens once, outside the loop, at the very end. You could say online learning is impulsive. It learns from one example and immediately changes its mind. Batch learning is more deliberate. It listens to the opinion of every single example before making a collective, democratic decision. So let's try it. Let's perform one update using batch learning and see what happens. We'll start from our original dumb weights. W1 equals 1, W2 equals 2, and so on. Okay, step 1 is the forward pass for all of our examples. We have to see what our dumb network predicts for everyone. Look at this table. We already did the first example, 3-2, and got a prediction of 37, which had a squared error of 169. Now we do the same for our other examples. For 1.4, the prediction is 33, giving a massive error of 361. And for 2.1, the prediction is 13, with an error of 4. The total error across our whole dataset is 534. Pretty bad. All right, step 2. Calculate the gradients for all the examples. We play the blame game for each data point, just like we did before. But here's the crucial difference. We don't update the weights yet. We just calculate the blame and put it in a table. For example 1, we already know the gradients. $520 for W1, $156 for W2, and so on. We just repeat that process for examples 2 and 3.
Now, for step 3, the part that makes batch learning special, we sum the blame and update just once. Look at the table. To get the total blame for 1he1, we just add up its column. 520 plus 380 plus 24 gives us a total gradient of 924. We do this for every weight. For 1he2, it's 324. For 1he3, it's it's 1,636. You can see all the totals here. Now, we use these total gradients to update our weights one single time. We'll use the same learning rate, 0.0001. Check out this update table. For 1he1, the new value is the old value, 1, minus the learning rate times that total gradient of 924, which comes out to 0.9076. We follow the same process for every other weight. This update direction is a compromise. It's the average best direction that helps reduce the error across all our data, not just one example. But did it work? Let's verify. This is the big test. We're going to do a forward pass for all 3 examples again, but this time using our new batch updated weights. The architecture is the same, but the weights have changed. This looks like a lot of math, so let's walk through the first example together. The target is 24. Before, our prediction was 37. Now, with the new weights, H1 comes up to 23.19, and H2 is 11.81. We plug those into the final equation, and our new prediction is 30.45. Hey! The old error was 169. The new error is just 41.6. It got much better. Now, here's the amazing part. Look at the other 2 examples. For the second one, the error drops from 361 all the way down to 127. And for the third example, the error practically disappears, dropping from 4 to just 0.06. All examples improve with a single batch update, one update, and it works for everyone. This is how a network learns to generalize. So, which one is better? Pure online learning is fast, but the learning is noisy and chaotic. Full batch learning gives a stable direction, but it's incredibly slow and memory hungry. Imagine trying to calculate and store the gradients for 1 million images at once. So what do we actually use in the real world? We compromise. We use mini batch learning. This is the sweet spot. It's the industry standard that powers virtually all modern AI. The idea is simple. First, you take a small batch of examples, maybe 32 or 64, then you update the weights based on that small group. Then you just repeat with the next batch. You can see the algorithm here. It's the best of both worlds. The gradients are stable enough because you're learning from a small crowd, not just one individual, and the memory usage is perfectly manageable.
This is how you train a network on a dataset of billions of images. You feed it one small handful at a time.
So now we have a complete, practical learning loop that can handle massive datasets. We have all the pieces. The only question left is, how does this simple process, which we ran on a tiny network with only 5 weights, possibly scale up to train a monster like GPT-4 with over 1 trillion weights? Is it really the same algorithm? The answer is the most beautiful part of this entire story. Look at this comparison. On one side, you see our tiny network with just 5 weights. On the other, GPT-4 with 1,760,000,000,000 weights. And yet, what's the process? It's identical. A forward pass, backpropagation, and gradient descent. It's the same 3-step dance. Scale changes everything, and yet it changes nothing. The stunning truth is this. You just mastered the core algorithm running inside
every AI system on Earth. ChatGPT, autonomous vehicles, medical diagnosis AI, they are all just scaled up, engineered versions of what we just built together from scratch. So, how do we get from our simple model to these massive ones? The core principles don't change. It's the same engine, just at a bigger scale. Let's break down how.
First, more layers and more neurons. This is the obvious one. Check out this table. Our network had 2 layers and 2 hidden neurons for a grand total of 5 weights. Real networks, they have tens or hundreds of layers with millions or billions of neurons leading to trillions of weights.
So, what does this change in our process? Almost nothing. It just means that chain for the chain rule gets much, much longer. The process, though, is identical. Second, we use more practical activation functions. In our neurons, we used x squared. It worked, but its gradient 2x can get really big and cause problems. Look at this table of a few popular ones. You've got RayLiu, which is super simple and fast. Then there's sigmoid, which is perfect when you need a probability between 0 and 1. They're just different tools for the job, but the core idea is the same. They're just a function we can find the derivative for. Third, we use better loss functions for different jobs. We used mean squared error because we were predicting a number, like a house price. But what if you're trying to classify an image as a cat or a dog? For that, you'd use something called cross-entropy loss, which you can see in this table. It's just a different formula for a different task. But here's the key. The specific formula doesn't matter as much as its job, and its job is always the same. Give us a single number to kick off the blame game. And that's it. That's the whole secret. You have seen the entire process. From Midjourney generating incredible art, to Tesla driving a car, they all use the exact same loop. Let's call it the universal pattern. 1. Forward pass. You make a guess. 2. Loss function. You measure how wrong the guess is. 3. Backpropagation. You calculate the blame for every weight. 4. Gradient descent. You nudge every weight in the right direction. And 5. Repeat. Do this millions or even billions of times. You started this hour thinking neural networks were an impenetrable black box. But now you know the truth. It's not magic. It's just a beautiful cascade of simple, intuitive ideas. Finding the bottom of a valley, tuning one knob at a time, and playing a clever game of blame. You've mastered the fundamentals. Welcome to the world of AI.